We have one more speaker for today I'm very excited to introduce to you, and that is Albert Greenberg. Albert is a corporate vice president at Microsoft. He's in the Azure Networking Group, which is the team that develops, engineers, and runs all of the systems and tools that power the Microsoft Cloud Network. He is well known as an author and a researcher himself, multiple awards, including a Sigmetrics Test of Time Award. He's a veteran of both Bell Labs and AT&T, where he was a principal in developing a lot of the systems and tools that AT&T used to run its network, and has done foundational work in developing the architectures and systems that are part of software-defined networking. So Albert joined us in 2007. He joined the Azure team. You joined, I should say, Microsoft Research in 2007. He joined the Azure team in 2010, and he's here with us tonight. And so with that, thank you for joining Albert Greenberg.
Thank you. Hi. So it's a pleasure to talk to you about startups. The startup that we're on is doubling every year. It's an amazing journey. And by the way, and thank you for coming. This, you'll see that I hope, I see a lot of faces that I recognize in the audience, and we have a beautiful new space. You'll find that we're open, and I'd like to see you more often than just in this room, and hopefully spend more time with you. So I'm going to try and describe the challenge of building a cloud and the expectations that we have for the cloud. It's really exciting to be on this journey to build the cloud. We see it as the platform for all the world's computing. It's a very inspiring task to build, and we see so much workload pouring on it, mission critical workload, hospitals, police forces. I mean, interacting with groups like that where they take reliability super seriously inspires us to even take it more seriously and understand what they mean by reliability and embody that in our DNA. So I'm going to talk about reliability, and I convince you, I hope, that reliability is the coolest thing that you could work on. Let's see, did that go? Okay. So one thing that at Microsoft we do, and I do in every one of my staff meetings and every one of our technical meetings, is talk about not just deep tech but deep culture. So, and I'm going to do that here, and I'm not going to bury it at the end. I'm going to talk about culture on the first slide. So, do a little bit of that. Then I'll talk about the open platform we're building for the research community. And then, give you some view of what Azure Scale means, and what it means to build mission-critical applications for a mission-critical platform for all applications on the planet, and how that causes us to rethink things in networking, and what an amazing opportunity we have to rethink and rebuild networks. And I'll just pick two things. I'll pick how we rethink device firmware, and how we rethink design and operations. Okay, so let me talk a little bit about culture. Again, we take it super seriously, and we talk about it all the time. And the connection to reliability is clear that monocultures are risky, right? Monocultures, people believe in the same vision, and they agree with each other, and they get it wrong. And I've seen it again and again. And diversity in our team delivers creativity, innovation, and lowers risk. So yeah, I talk about diversity all the time. Just to give you, we have a long ways to go, in our industry. But also, the encouraging thing is we're putting a focus on it. And so, for example, we just when we spin up new teams and new initiatives, we set as a target 40% diverse hires, and we hit it. So we can do it, and it's great. It's working out for us. We're not there yet. We're trying to get better, but I wanted to give you that update.
My favorite aspect of working on the Open Network Emulator user interface was that I got to learn how to use AngularJS in the building of a website. The great communication and unity of my team was what helped to perfect my skills that I had learned.
My internship project was an interesting blend of formal verification and emulation. I love the fact that I could work at the intersection of cutting-edge research and engineering, that too at an Azure scale, and that's what excites me the most and brought me back in a full-time role here on the Open Network Emulator team.
I should have given you a little bit of preamble before showing you the video. That was a video of an intern we have now and an intern that's I think I saw her in the room, that created the emulator that I'll tell you about. So one thing that we want to do is encourage you to collaborate with us, work with us, and continue to send us interns. I can tell you, in my team alone, we're hiring 90 college hires. That's our target in the U.S. and more in other places around the world. Okay, so we spent just $7.5 billion recently for a company called GitHub. We are committed to open source, and this is just what we call the NASCAR diagram of the different open source projects we have. I was glad to see Databricks. Databricks is one of the customers, and they're also based on an open source project. So we are, it's the new Microsoft, we're open, we love Linux, we love open source. And I think the GitHub acquisition speaks 7.5 billion times. So one thing I want to announce here today really is the open sourcing of an emulator that I'll tell you about called the Open Network Emulator 1. And it will be available, it's a little bit of a pre-announce, it'll be available January 2019. And I'll tell you about what it provides for you, and I hope it'll excite you. It'll provide you a way to really emulate cloud scale, and I'll tell you what I mean by emulation in a minute. And it provides hands-on experience for students on the real router software. I'm talking about thousands of routers and switches, real networks, and create large-scale labs on demand, test your next research idea, and go as deep as you want in building networks. And they're the real networks, but you don't have to buy the hardware. You can run all this stuff on the cloud, our cloud. So, and this emulator supports both commercial, the normal sort of sets of companies that you think of in networking, and our own open source switch firmware called Sonic. And these are, the word virtual is in here. It's the real thing. It's not modeling or something like that. It's the actual software that runs on the device. And it'll be available in the marketplace. Just start at portal.azure.com and you'll find it. And there's the contact. By the way, I'm Albert at I'm Albert at Microsoft.com. Excuse me. And you can email me for other things. Okay. So let me tell you a little bit of Azure Scale. Mark Rusinovich may have gone through some of this. What it means, these numbers I have to update all the time because we keep growing. I think at the bottom of Africa, we just added some new data centers and regions. We're in 54 Azure regions. We're all over the earth. We've deployed 70,000 miles of fiber in 130 locations. We have 130 global edge sites. These are the outer ring close to the metros where we can reach the rest of the internet. And just sort of a fun fact that we think that we are such a large network. We deploy more technology than any telco you can think of, and probably any cloud you can think of. So we deployed more, for example, 100G dense wavelength division multiplexing links this year than the rest of the industry combined. So we are building a huge network. Areas of innovation. One that I'll talk about today is we take an algorithm and data-driven approach to network design and operations, and it's deep. It's not modeling on the side. It's in the guts and the actual mechanism how we run and design the network. And we innovate in optical technology. This thing would have been cost prohibitive if we had just used off-the-shelf technology. And we innovate in our own software defined network. It's nice, I hope some of you or your interns get a chance to visit one of our data centers just to get an idea of the scale. It's it's incredible scale. So like, there's Dave Maltz in that little car down there with the circle around it. Just kidding, but that's the scale thing there. And there's the big data center. It's enormous scale, and that's just one of the data centers in the region. In terms of mission critical, again, I'm going to talk to you about reliability. We support 90% of the Fortune 500 on the Microsoft Cloud. These are just some of the names, but it just brings home that reliability is so key. These people haven't just taken their small test labs or something like that and put it in the cloud. They've put their core business in the cloud because it doesn't make sense to build it on-prem. And they support a lot of things are born in the cloud, and other things are connected to the premise. But this is how these companies build and run their world, and it's how, again, the critical government and medical infrastructure runs the world. Right, so we connect to we have a private connectivity offer that is taking off like crazy, where you want to have one relationship with Microsoft with different access providers. These are some of the access providers where you can get private connectivity straight to the Microsoft Cloud. And this chart is also growing. So we reach everybody with high speed, privately and over internet. This is just something I often show, and we believe in Azure. What is the hierarchy of needs for the cloud? What are the basic things? And it's all about, at the bottom you have to be secure. If you're not secure, then you won't trust running your critical apps in the cloud. So that's at the very bottom, and we spend a lot of time on security constantly. Reliability is the one I'll talk about today. It has to be supportable. You have to be able to, just use it, and it has to just work without a lot of thinking and trying to figure it out and calling us up. And it has to work the way you expect it, and it has to be fast. So those are my priorities, and I'll, in this talk about reliability. And I'll talk about just two. There's a wide set of work on reliability, but I'll talk about the device firmware and talk about Sonic, which is on GitHub, and I'll talk about the network emulator, also on GitHub. Will be on GitHub for you to download. Okay, so let me start with Sonic. So if you think about the world of networks, it's changing in a very exciting way. So it had been that you'd buy this monolithic box from a networking vendor, and all the things that I highlight here in blue, you would not have. You really want to run your network and consume your software the way you do cloud and other computing artifacts. You don't want a big proprietary box that you can't change and grow. So you want agility. You want to be able to, like in the cloud, we ship weekly. When there's a bug, we take care of the bug right away, within hours or as fast as we can roll it out, a bug fix. It has to be serviceable. This is something that I don't know if academia studies enough. Serviceability, it's so critical. You have to be able to update. It goes with reliability and the velocity. You have to be able to update without anybody noticing. You have to be able to update all the time. Things have to be modular, so you can do these hitless upgrades and restarts. And it has to be as simple as use a normal sort of container update to reload the OS image. It has to be something you can already do and reliable, which I've talked about. So two things here. One is we're getting a lot of help from the industry. So there are these companies that are producing amazing merchant silicon. These are ASICs that are fairly cheap and can do everything you'd like to do in networking. They have super high speed. They have lots of ports. They have the right kind of buffering. They have incredible capabilities hidden. You may not know about them, but the ASIC supports them. And if you can just get access to that ASIC. And at the same time, you want to protect, you want to protect your software that runs above that ASIC. So you need some sort of hardware abstraction layer that allows you to plug in any ASIC below. Your software keeps working, but you can still get to the unique features of the ASIC below. And we have something called Switch Abstraction Interface, which provides that. And I'll tell you, it's really working out. So we don't have to go with just one ASIC vendor. We can go with several. It's again open source. Go to GitHub, pick it up. It's open source. It's supported through the Open Compute Platform. Provides essentially the .h files for your code. Common APIs, which are then implemented by drivers beneath it, depending on the ASIC. It supports disaggregation. You don't have to buy this monolith. You can get the ASIC, buy the board, get the whole thing manufactured and build your own router. So the software and hardware can evolve independently, and there's an open community around it. So above this SI, we have something which was definitely named in a different way, so you would remember it, called Sonic. And that's the software that really operates the switch. And that's what we use in Azure. So it's also available through OCP. It provides everything you need in terms of functionality. I'll tell you a little bit more, but it really allows you to run your network devices like you'd run a cloud service, like you'd run software in general, yet you can do networking. So it really opens up the world to be able to change things and get at the power of these ASICs and really enjoy the disaggregation that the industry is providing. So here, this is just the kind of network we build to support our regional networks. Well, it's a Closs style network. Closs was a Bell Labs mathematician in the 50s that figured this stuff out and did a good job. And so there's a lot of regularity here, a lot of power here. So it's like RAID for networks. You have lots of components. Things can fail. It's okay because you've got more things that are working. Yet you can have full bisection bandwidth. You basically can go from any point in a region to any other point without congestion. And that you need software running on those switches, and that's where we run Sonic. So it shows the Sonic software there. Now, one test of, it really is, you're really managing your software like you would manage, or your network software like you'd manage software services. Just stuff works that you'd expect to work. Like down at the bottom, there's Redis DB. It could be any kind of caching service you want. So in networking, the very simplest things like getting counters out of a box. In the old school world, there's this protocol called SNMP. Back in the day, 20 years ago, when it was invented, it was awesome. But now, every time you want a single column in SNMP, the IETF meets. Maybe they don't accept it. Maybe they do. Maybe you beg your vendor to get it in. Maybe they do. Maybe they don't. It's just counters. What's the big deal? So you can just reflect. You can put a Redis agent on the switch, and it can just export whatever counters you need, and push, pull. All those options are yours. So there's the typical networking applications on top of the operating system, as well as orchestration software and telemetry software, Ansible, which we use, Puppet, Chef, and so forth. So how does it relate to, I mean, we wouldn't do this project if it didn't improve reliability. So today, we don't have control. If we go to a commercial vendor, we're convincing. We're building the world's biggest cloud. We have big pockets, wallets or something, but we can't control the quality of what goes in that software. Sonic gives us that control, and then really, it's still hard work. Software is hard, but we don't support every feature. We just support what's needed for the cloud applications. So we minimize the baggage that goes along. And then, we're free to pick and choose, cherry pick what software we want to go with. And every cloud provider that consumes Sonic, and every one of you, if you consume Sonic, can pick your software. Hitless upgrade is huge for us. We want to be able, if there's a bug, take care of it. If there's a feature we want, take care of it without you as a customer noticing. So we can fix bugs and do fleet-wide security patches in hours and new features in days. And yeah, we put the pressure of the entire cloud on the software, so it's battle tested, open source. So it's working out, as I said. We have a lot of community. We spend time on community. In the top right-hand corner are some of the companies that are also heavily invested in Sonic. We work with the other companies to run their software in the Sonic framework, and some of the in the middle right, my right, companies that do the ODM world. They build the devices that make up the hardware of the switch, as well as on the left middle, the OEM world. Some of them anyway, like Arista, that build a device and sell it directly. And then below, we have all those ASIC manufacturers, and Cisco as well, all part of the community. So, really, it's an invitation to you. If you like networking, or you think you might like networking, you want to experiment in networking, you can consume Sonic. It's very pleasant, I think. It's containerized, it's Docker, and it's familiar. It's Linux. It's what you know how to do. You can just consume it and make it work. So try it. And you can find it by web search, or you can just remember this GitHub URL. So I'm going to change now from, we did this network firmware because we wanted greater control. We wanted to improve reliability, and we wanted to take care of all the bugs themselves. We wanted just the features we needed to improve reliability, but let's now think about the big network. Let's think, how do we build a network that is reliable by design and meet these goals? Changes work as intended, it's resilient, we minimize the impact of changes, it learns and adapts automatically, and we can verify with formal methods any gap between what we intend the network to do and what it actually does. And you saw all those links there, right? There could be little defects in the optics. We have to be able to detect those little defects, needle in a haystack type problems where we use machine learning. So we have a set of projects and a set of collaborations with Microsoft Research. In fact, all this stuff that I've talked about was either born in or worked. We worked together with Microsoft Research to bring to Azure. And I will talk about the top one and maybe the second one. But email me. Again, it's albert@microsoft.com, and I can give you the pointers to all the others. So, this is another, slide about some of the challenges that we face. If we need a fiber nowadays, or we need more capacity between 2 points, we design that whole thing. We run a boat. We pull the fiber across the ocean. Our team does that. So we take on that. It's about like about as routine as you might take, plug in an Ethernet cable. We run the boat, pull the fiber, and we're ready. But we have to be resilient to storms, typhoons. The fiber somehow gets the sharks excited, and they like to bite the fiber. There's repeaters down there. Sadly, there's fishing that catches the cables, and there's potentially sabotage. So it costs a lot of money to run the boat out, to pull the fiber up, fix it, and sink it back down. So we think a lot about optimizing for resilient design so that we don't have to rush the boat out. We have enough fiber in the right places that it's okay if some of these disasters happen. And Netsim is one of the projects that allows us to understand the impact of any failure on the fiber. Okay, so let me tell you about that a little bit, and then I'll get on to the One Network Emulator. So one theme that I want to convey is a lot of the stuff we do in networking to make the network reliable is stuff that you cannot do without a cloud. And the amount of hours and the computational methods we apply are cloud methods. And we need VM hours to do this. So we simulate, these are modeling, like math model simulations of the network, covering literally millions of contingencies for every fiber of things that could go wrong. And there's a pipeline here and timelines. So think about if you use Azure, you're running Azure Batch every time you think of a project. And you pretty much, this is what the cloud job is all about. You try to anticipate all the things that could possibly go wrong. Get that risk into the model, and then simulate all these things and see if you're resilient to them. And that's just routine for us. We run these simulations before we touch the network, and as we design the network. And here's an example. We created a fiber path with partners, and it's a bit unusual that it lands in Spain. Most of them land north of Spain, but we want diversity, so we land in Spain, and so we run it from the Virginia, DC area into Spain. And just in this case, we had to think about, as we designed this thing, thousands of different possible combinations of ways to design and protect the fiber and minimize disruption as we went. And for that, we ran the Netsim simulator. So there's lots of cool videos on the net. If you can look for Maria cable, and you'll see different government officials and Microsoft officials talking about this cable. And if you can also find deep technical talks from my team on how we built this cable. Now I'm going to talk to you about the kind of work that it's more detailed work, the kind of work that happens day to day in operating the network. And it's not a bad analogy to think about, flying an interesting plane. Except, while the plane is flying, you're changing the plane, and you're adding engines and taking away engines, and the wings and wheels are changing, and so forth. So it's a evolving plane in flight. And but the consequences, again, the reliability has got to be there. The reliability constraints are so strong. There's no way that plane can go down or even be disrupted. And we need an emulator. We need to train our people. We need to have the kind of confidence that when they're making a change to the network, and really people's lives and work depend on it, that it's going to work. And so we need something like a flight simulator. So we built one, and I will tell you a little bit about it. And this is the open source thing that you can consume starting in January. You can simulate a network with Fidelity. You won't be able to tell if it. You can bring in your network engineer and let them go at it and give them a kind of a Turing test. Is this the emulator or is this the real thing? They won't know. You can do that with thousands of devices in minutes. It's seamless, it's easy to deploy, and it's, again, high fidelity. So just, do we use it? We spent 12 million core hours on Azure Network Emulator. Before I came here, we were running it for a big network migration that we had to do. So by the way, because of this emulator and the confidence it gave us, we did more network migrations. We changed everything in our network. We moved more, we pulled more cables, we changed more routers and switches. We did more stuff to the network in the last year than we've ever done before. And it was probably the biggest network migration in anybody's history, and nobody noticed. But we caught 100 or so bugs in this emulator, and that's why nobody noticed. The bugs never got to production. So, the way it works is a network engineer describes a change in a machine-readable form. We automatically, we could pick what vendor software we want. It's the actual vendor software and our own software. Then we download it into the emulated replica and run it. We also use theorem-proving technology from MSR, as well as the emulation. And we find out if the intent worked as we expected, the intended change. Let me try to click through this. I don't have time to simulate myself. Okay, so one problem you have with these emulations is, how big a network to emulate? Are you going to, where's the boundary? Are you going to go for the whole internet? Where do you draw the line? Do you have to do the whole data center? Well, you need this fidelity. You need to be able to answer the question that, is this change safe? Is it going to have the intended impact? So part of the research on this had been, how do I draw the smallest boundary so I can answer the question without emulating the entire internet? And that's what we do. So we pick an economic frontier and emulate inside it, and we do that all the time. And that's described in an SOSP paper from this year. Okay. Let me say one other thing about it. So again, I want to just tell you how high fidelity it is. If you imagine like you're an engineer at one of these device companies, and you don't expect your software to sort of go to sleep and wake up in the cloud and still work. It expects, hey, I'm a device and I've got these wires and I'm going to check the health of those wires and I'm going to run some diagnostics. And all that has to work. That software has to be faked out and fooled and understand that the emulated hardware is just like the real hardware, and that's what happens here. So that's part of the interesting engineering problems. Why does that work? It's because of the cloud. It's because of virtual machines. Same deal with virtual machines. Virtual machines think they're on real machines. It's because of virtual networking. So we had to figure out all that tech. That's why it works now. It didn't work 5 years ago or 10 years ago. We have the mechanisms. Because we can virtualize everything to full fidelity in the cloud, we can also virtualize the networks and do this emulator and then use the cloud to run the emulator. That's why it works. So again, try it. You'll be able to, you can email the developers now to get early information about it, and it'll be on Azure Marketplace. So this is an open invitation for all the work. Try Sonic, try the emulator. All right. I think the appendix, which I'm not going to get to, has to do with all those other projects I don't have time for. But it's really an exciting opportunity to rethink the basics of networking. I don't know how to directly or somehow chemically or viscerally convince you that reliability is the most cool thing to work on, the most important thing to work on. But if you start to think about, changing all of computing to run in the cloud, and then just, recurse on that and think of what does that mean? What all the startups, all the already started ups, all the work that you see pouring in the cloud, all the AI and machine learning, then you'll see that reliability is really a hard problem and deep and takes years of work, and we need you to help us get there. All right, I'll wrap it up.
Thanks, Albert.
All right, thanks.
Well, thank you again, Albert. It's amazing when you consider the scale of challenges and opportunity in networking that you're representing today. And hopefully that gives you some potentially interesting pointers to how to pursue your own research, and as well as to guide research and instruction for your students. So we are at the end of day one. Thank you for a fabulous day. I hope it was worthwhile. I hope you enjoyed it. Just take a moment before we head off to what I expect will be a really nice dinner tonight at the hotel. I want to give you a little bit of a recap of what we've done and a preview of what will happen tomorrow. So I was really happy that we were able to announce here for the first time today and to give you input to some new fellowship opportunities, both the student fellowship as well as invite your input to the young faculty fellowships, which we'll be bringing back soon. I appreciate the fact that Albert was pre-announcing for you all the Open Network Emulator 1 that'll be available in January, and hopefully you caught the email address if you'd like to get a hold of that ahead of time. We had a lot of really top-notch plenary and breakout sessions today. I was super pleased with those, and again, thanks to all of the people who prepared so well to deliver on that. I hope you had an opportunity to enjoy some break time and to network both with old friends and to make some new friends. So we have more of this to come again tomorrow. Tomorrow we'll be doing much the same. We have one interesting thing, though, that we will add to tomorrow. We have a technology showcase, which is actually going to be across the hallway tomorrow. It's a bit of a poster session to show directly some of our researchers and some projects that they're working on, gives you an opportunity to engage directly with them. We'll introduce you to those very broadly in what we call a lightning round, where we'll have them come up and give you just a 1-minute overview so you can get both the breadth of what we're doing as well as have the opportunity to engage deeply with the researchers and the projects that we highlight there. Tonight, I'm looking forward to joining you all at dinner. Harry Shum will be there. Eric Horvitz, of course, will be hosting. There will be a bag check at the hotel, so when you get there, if you're not staying at the hotel, you just want to use a bag check, there's a bag check there. Buses will be out front. We've got a couple of buses that are specially marked that have a trivia contest on them, so if you particularly want to or don't want to be doing trivia on the ride home. I had 2 jobs, as I said, one of which was the weather, which I'm hopeful is still going well out there. The other was traffic. I'm still working on that, but maybe Albert can help me with some of the traffic management that we have to do. But I am looking forward to dinner tonight. We'll hopefully have you as well for a group photo tonight, so it'll be a lot of fun. One other way I'd love for us to be able to say thank you to you is when you do check in, we'd love to provide you with a new smart speaker. So we've got the Harman Kardon Invoke plus Cortana speaker as a gift for you all. So thank you again for joining us here today. The buses are out front. We will be back here at 8:30 in the morning. If you enjoyed what you heard today, be sure to communicate with us on all of those properties. Hashtag is MSFactSum. We'll see you at dinner tonight and here again tomorrow morning at 8:30. Thanks for a great first day.